All right, so now let's talk about correlations. Correlations are just examining the relationship between two continuous level variables. And when I say continuous level, I mean interval or ratio level variables. And I say continuous because there's like a lot of range in between. You can look at like say 1.5 and that makes sense. Whereas the nominal and ordinal level variables do not make sense when you look at numbers like in between the categories. All right, so for correlation, we have an R as our coefficient. And that is what we use to indicate the value of the correlation. And it ranges from -1 to 1. If we have a negative R, that means that as the independent variable increases, the dependent variable decreases. Or you could have the opposite with like the independent variable decreasing as the dv increases. If you have a positive R, then the IV and the dV are going to increase together or decrease together. So I'm going to show you some graphs in the next slides that show this relationship and make it a little bit more clear. Some of the limitations of the correlation is that you can only have two variables. It is only a linear relationship, so if you have a curvilinear relationship where it goes up and then comes back down, that's not going to be tested here with that correlation. And you obviously cannot make any kind of causal inferences because we have not performed an experiment. All right. So here you see the positive relationship. Both variables go up at the same time. A negative relationship, we have as the independent variable goes down, the dependent variable goes up. And here we have a no relationship whatsoever. All right, and then when you are interpreting the R coefficient, there you can tell both the direction of the relationship, so is it negative or positive, and then you can also look at the magnitude of the relationship, so how strong is it. And we have some categories here for the strength of an R coefficient. Anything below 0.3, whether that means it's -0.3 to 0 or positive 0.3 to 0. Anything in between those two is weak. Then we have 0.31 to 0.70, that's moderate, and anything above 0.70 is a strong relationship. This is a correlation matrix. Oftentimes in most studies you will see a correlation matrix that's supposed to just give you an idea of how the variables in the study are related to each other, even if other analyses are going to be run. So here we have some variables, and if you look at the first R value, that's -0.46, that shows that there is a moderate negative relationship between socioeconomic status and the approval of the ban. So you're just looking at the numbers that are listed on the left-hand side of the table to figure out which variable is being tested as the dependent variable or independent variable. With correlations, one thing that I didn't mention is that you often can't tell what the independent variable is or what the dependent variable is, right? It probably isn't going to matter what you label as each because they are not always measured in time, as in like the independent variable is generally measured at the same time that the dependent variable is. So it's not necessarily the independent variable. You could have a relationship between these two variables and not really know which one comes first or which one caused the change. So keep that in mind when you are answering questions about correlations and regressions, actually. You often can't tell which one's the independent variable and which one's the dependent variable, and it doesn't really matter which one's which. So the major difference between a correlation and, for example, a simple linear regression, because correlation and simple linear regression are actually basically the same. The big difference is that a correlation describes the strength and direction of a linear relationship between two variables, whereas in the formula for a regression, it's trying to predict the value of a dependent variable for any value of the independent variable. So that's a major difference. Most of the time, your numbers for a correlation and a simple linear regression are going to be the same, which is why in many of the assignments and then the test, I group them together, correlation and simple linear regression. We have other regressions that are not the same, which we'll go over here in a second. So a regression, this shows how we calculate a regression. We are looking to try and predict values of the dependent variable based on values of the independent variable. And this is kind of just stuff that you don't really need to know, but it helps you to understand how we get the regression line. We are trying to reduce the amount of error we have in that line. We're trying to find the best fit for that line based on the data that we have. So each one of those dots represents a person reporting both the independent variable and the dependent variable. And we are looking to find a line that reduces the space between those dots and the line as much as possible. So something that's in the very center of all of those dots. So, which one is it here? All right, so now we get to multiple regression, and don't let this image scare you. But when we look at relationships between multiple variables, we are kind of looking at its relationship over a 3D, 4D, 5D plane, right? So it's hard to graph these relationships. And we often just don't really try to do that, right? Because that wouldn't make a whole lot of sense. But this is what it would look like if we were looking at these three variables and trying to graph it. So with multiple regression, we are testing multiple independent variables and trying to predict the value of a dependent variable. All of these variables are continuous, meaning they are either interval or ratio level variables. Same with regular correlations and regressions. We can't make any kind of causal inferences. So the relationship is often bidirectional. We don't know which one started the effect, right? It could be one is the IV, one is the DV. We're obviously going to hypothesize that one is the IV and one is the DV, but we don't actually know which one came first or which one caused something. Some assumptions of multiple regression. One is that you cannot have multicollinearity. What that means is that you don't want many variables that you are entering into the formula to be highly correlated. If they are very similar variables, then you won't be able to tell how much one variable can influence the dependent variable over the other variable, which is very similar. Here you can see in the pictures why that's the case, right? If we have two variables that are pretty similar, like X and W are in the right-hand figure, then there's going to be a lot of overlap between them, and we won't necessarily be able to see which one causes what, or how much one is related to the other. it kind of messes with the formula too. Oftentimes, if you have multicollinearity, then you will not find a significant result. Or the formula, when you put it into the statistical software, it'll just throw it back at you and say, no, I can't do that. When we are running a multiple regression, we are looking at explaining the variation in the dependent variable. Why? So let's say we're looking at relationship satisfaction. We want to know how much time spent together and the amount of sex plays into one's relationship satisfaction. So X is time spent together, W is the amount of sex. Those may be somewhat related, right? The more time you spend together, the more opportunities you have to have sex. So there might be some overlap, but they're probably pretty separate. And then we have a whole lot of other variables that could explain the your relationship satisfaction. That is pictured inside the rectangle, but not in any circle, right? So it's just the area within the rectangle. So when we're running the multiple regression, we're just looking at A, B, and C. We're looking to see how much of the variation in Y, so how much of people's relationship satisfaction can be explained by just time spent together, by just the amount of sex someone has, and then how much can be explained by both of those together. And that's what we call shared variance, which is the overlap between the two variables. We get another coefficient with multiple regressions, which is called the R-squared. This tells us the percentage of variance in the DV that can be explained by the IV or multiple IVs. So in order to get this number, all we really have to do is square the R. So if we had a correlation, we could get that number. We just square the R, and when we do that, we can see how much percentage of the variance we're explaining with the independent variable. So here I show you the R is 0.4. That's a moderate relationship between the variables, and our R squared tells us that 16% of the variance in whatever DV it is can be explained by the variables we looked at. It also shows that 84% can be explained by variables that we did not measure, right? So that's an interesting fact as well. This is just showing shared variance. Here's another way to look at multiple regression. When we are interpreting the multiple regression coefficients, we have several, right? We have the unstandardized B, which is, or beta, which is for every 1 point change. So let's say we measured something from 1 to 7. That means every time we change from 1 to 2, 2 to 3, 3 to 4, every 1 point change in the independent variable, we get a plus or minus change in the dependent variable. If we measured the independent variable and the dependent variable using the same number of intervals, if they're both interval, then we can report the unstandardized beta, and that will make sense, right? Because they're both measured on the same scale. But if we don't have them both measured on the same scale, maybe the independent variable was 1 to 7 and the dependent variable was 1 to 10, then that becomes problematic. We can't really know what the change looks like using the unstandardized B. So then we have to report the beta coefficient, which is basically the same as your R for correlations. And that shows the direction and the magnitude of the relationship between the IV and the DV. And it's really just looking at one unit change. So the unit can have all different numbers. We don't really need to know what the unit stands for. We just know that for every unit in the independent variable, we see a plus or minus in the dependent variable. And the reason that we report it this way is because what this formula does for multiple regression to give us the beta coefficient is it standardizes the variables. So, so that they can be compared on the same level. So one unit change, the unit size doesn't really matter. We just know that they are now comparable scales. The regression coefficient is a capital R. This does show the direction and magnitude still, but oftentimes the regression coefficient for a multiple regression is going to look at all of the independent variables together and how together they explain the dependent variable. Then we have the squared regression coefficient, which shows the amount that all of the independent variables together explain the DV. So it's usually a percentage, right? 0.16, like we looked at before. It would still be interpreted as 16%, but it would mean that all of the independent variables together explain 16% of the variance in the DV. This is just showing a table reporting multiple regression results and where you can find the numbers. Then we have hierarchical regression. This is the last type of regression. It's very similar to a multiple regression. It's actually a type of multiple regression, but what you do with a hierarchical regression is you put variables into the formula in the order that they are predicted to occur. So you get to see how the R value changes when you add one or two variables to, for example, maybe some control variables that you had. So let's, for example, think about this hypothesis or this research question. Does television viewing predict sexism over and above the influence of gender and education? So we're looking to see whether gender and education impacts sexism, right? Then we add to that formula television viewing to see if television viewing can predict sexism more than gender and education. So when we are interpreting the hierarchical regression, we have something called R-squared change, and it's usually pictured with a triangle. So it's gonna have triangle, capital R squared, that means R squared change or change in R squared. And that is gonna show us the amount of variance that is predicted in the DV based on whatever IVs we added to the formula. So I'll show you, I think, an example of this here in a second. But yeah, here we go. So the R-squared change shows the additional variance that can be explained when you add variables to the equation. So in this table here, you can see that ROM, or preoperative total KSS, has an R-squared change of 0.049. So this is like the initial R-squared, which doesn't really help us a whole lot. But if we go on to look at this next category, preoperative ROM, we can see that over and above the 0.049 that the preoperative total KSS predicted. Wow, this is just like the craziest freaking table ever. But over and above that, we can see that preoperative ROM predicts 3.4% of the change in whatever dependent variable it is. I guess surgical outcomes. All right, so interpret that.